Hi, this is an example problem on projectile motion, another type of problem where we're going to apply vector mathematics to physics. In projectile motion, we've got two-dimensional motion in which an object is moving in the air, and it is the only acceleration that it experiences is due to Earth's gravitational acceleration, and that means that the acceleration is constant. In other words, this is a constant acceleration problem. So we're going to use similar methods as we did in chapter 2. Now we've got to use vectors as well. So if we think about constant acceleration, we can come up with these 5 different variables that describe the motion. We know that the acceleration is constant, but notice now that it's got 2 components, an x and y. So we're going to have 2 constant values for ax, ay. In fact, they're always the same for projectile motion, so if it's a projectile motion problem, we'll know. Similarly, we've got initial velocity, final velocity, a displacement, and you can see the components of those here. Finally, the 5th variable, the elapsed time, delta t, it's a scalar. Notice that it doesn't have a column in x or y. It is the same number for both components, and it plays a special role. It unites the x and y components, as we'll see in the problem. So take a moment and read the problem. Pause it for a second. Now that you've read the problem, we're going to go ahead and look at some preliminary stuff. So first of all, I want to highlight that the the package is in the airplane, but it's released. And then it follows this dashed line, which we call, again, this is the trajectory, right? This is the path that the object moves through in the air. Whenever we're doing constant acceleration problems, we are always very much interested in the starting point and the ending point. So we're going to go label those two, and we start here, and we end here. All right, now in part A, we're asked, how far from the point of release does the package strike the ground? We might not know what that means initially, so I've written there next to it what it really is asking you for. What is the magnitude of the displacement? So let's go ahead and draw the displacement vector. You always start at the initial point, and it's a straight line that is going to be drawn to the final point. So here it is. There's your displacement vector, and we'll put a little arrow on it to show you that that's where it ends. We call this guy again delta r, and the magnitude of that, how long it is, that's your delta r. We can write it like this if we want with absolute values, and that's what we're trying to look for in this problem. Now, before we get further in this problem, I want to stress that as we do the math, it's essential that you work just with the vector components when you're solving the equations for constant acceleration. So I want to start by writing down our 5 variables and leaving spaces for the components. So here's a table that I like to use to organize my work for this problem, with the 2 columns for x and y for the vector components for the 4 vectors. And notice for t that there's only one spot because it's a scalar. It's the same for both columns. Now, to be able to fill out the vector components, we need to draw the vectors first on the picture. So the initial velocity occurs at the starting point, and since the package was moving with the plane initially, it is going in this direction, our initial velocity with the plane to start. Now, this direction for the initial velocity, it's important to note that by looking at the trajectory, we can always figure out where the initial velocity is supposed to be pointing in. The trajectory was initially like this, and then we start there. Notice that it's tangent to the trajectory, the initial velocity. And so now, if I want to draw the final velocity, it occurs over here at the end. And if I look at that trajectory, right, kind of maybe extend a little bit what it might look like, right? We're going to draw a line tangent. That means just touching parallel at that point. And let's go ahead and put the arrow tips on our initial and final velocity vectors. So here's your v initial, and here is your v final. And I'm not going to write the f this time for v final, but that's what it means. I want to point something out here that v final is the moment before you hit the ground, right? Once you hit the ground, the acceleration has been changed drastically. It's no longer just due to gravity. And finally, we need to go ahead and draw the acceleration vector. I'm going to draw it right at the start there. It actually, you know, it's the same everywhere. So if I want to draw it right here, it's going to be like this. Point straight down. That's always the acceleration for free fall. Earth causes things to accelerate straight down towards it, as if you dropped a rock or something like that. And again, it's constant. So if I want, I could draw it again over here. The fact is that it never changes. And so again, our goal to fill out the columns for the x and y, we always get a free one with projectile motion. We know that a gravitational acceleration is 0 in the x direction, and it's negative g, minus 9.8 meters per second squared in the y direction. And now the game is the same as before. We need to get at least 3 unique bits of information in one column, and when we do that, we can go and use the equation of constant acceleration. How are we going to figure out the components? Which of those that we have numerical values for? We've got to plot the vectors and figure them out. So let's start with the displacement vector, okay? So I've drawn the displacement vector in its own graph at the origin. And now I'm going to try to figure out if I know any number values for the components, delta x and delta y. Turns out that we do know what delta y is, because it says it starts 100 meters above the ground, that it ends at the ground. So the y component is going to look like this. Goes down, and delta y equals, since it went down, it's minus 100 meters. Now delta x is going to be this guy to complete the right triangle. We don't know what delta x is yet, so that's something we're going to have to figure out. But we can go ahead and write down delta y here, minus 100 meters. And hey, we got 2 things already in the y column, so that's not too bad. Next, let's go plot the initial velocity, because we're given some information over here about it as well. We know that the plane with the package in it was traveling 40 meters per second horizontally. So let's graph that initial velocity vector. So I've graphed the initial velocity vector right at the origin so we can clearly see it and figure out its components. And you know what? Pay attention to this one. This is one of the best ones. When you see this, you can do your dance, because this is easy. Vx, Vy. It only points in the x direction. Therefore, V initial y is 0. All of the speed, 40 meters per second, points in the positive x direction. So we put that right here. And we can go fill this out into the table. So V initial y, 0 meters per second. And V initial x, plus 40 meters per second. Now, while we're at it, we know that the acceleration in the x direction equals 0, right? And acceleration is the change in velocity. And if there's 0 acceleration, the velocity in that direction will never change. Therefore, at the end, the x component of velocity, it is still the same. So your final x velocity is still 40 meters per second because there's no acceleration. Now, looking at our chart, we see that we have a lot of data. In fact, I've got 3 things in the y direction. I've got 3 things in the x direction. However, 2 of these are not unique. This is the same as this. So really, I've only got 2 unique bits of info in the x direction, whereas I've got 3 in the y direction. So we are set. We can start to solve for things in the y direction. And in part B, we're looking for the magnitude of the final velocity, otherwise the speed, and we're looking for the angle of the final velocity, the direction. We're going to need to get this guy here, right? So let's solve for Vy final first. So at this point, we're going to go and look for an equation that doesn't have delta t in it in the y direction. And here we have all the equations for constant acceleration. So in particular, we are looking for let's see, the one that doesn't have t. Looks like it is the 5th equation there. So let's go ahead and write that down. So here's our equation number 5 for the y direction, and we're going to solve for Vy final. If there's any zeros in the data column here, let's go ahead and plug that in. So, this is 0. Get rid of that right away. And now we can solve for Vy, right? So we're going to go ahead and write that down. Let's take the square root of both sides. And when we do that, we're going to end up with Vy, I got to do plus or minus here, is equal to plus or minus the square root of 2a delta y. Let's plug our numbers in and calculate. So I've plugged in the numbers, And notice I had to put the signs in correctly, and I end up getting an answer here, but I'm still not sure which one am I going to choose here. Is it going to be the plus or the minus sign? To figure that out, again, graph your final velocity vector and look at the direction of the components to determine it. So here's our final velocity vector. Let's make our components. So here going down is our Vy final, and here going to the right is our our Vx final. Here's our right triangle, the hypotenuse, that's the speed. And hey, we can see Vy is negative, so we're going to go back here and we have to choose the negative value. And so a quick check on the signs here. This is a fourth quadrant vector. We know that x is positive, good, y is negative, good. And so now we know what Vy is here. It is equal to minus 44.3 meters per second. Now look at our table. We know everything except for delta t and delta x. I can solve for delta t in the y column here, and then I can use it in the x column, and I can solve for delta x. So that's what we're going to do here, okay? Since we know so much information in the y column, we can pick any equation practically to get delta t, and let's pick an easy one. So I'm going to go ahead and pick the top one here, I think. Vy equals v initial y plus ay delta t. Now we know this value, this value is 0, and we're going to solve for delta t. So let's just do a little bit of algebra here. If we rearrange this, we're going to get ay delta t is equal to Vy. Let's divide by ay on both sides, cancel those out, and we're going to see that delta t is equal to Vy divided by ay. We know the numbers, Vy minus 44.3 meters per second, ay minus 9.8 meters per second squared, and when we solve this number for delta t, we end up getting this. And our units are right because we canceled the meters. In the lower part, we canceled one of the seconds below, and that inverse seconds becomes just seconds in the numerator. So we can also put that now that we know what delta t is. It's equal to 4.52, and the key idea is that this applies to both the x and the y direction. Finally, let's go ahead and use an equation to solve for delta x. We know all the data, we can pick the easiest one. Why don't we try equation number 2? Delta x equals 1/2 v naught x plus vx times delta t. So here's our equation. And in fact, we know all the values here. All we got to do is plug them in and calculate. So let's do that. So plugging in our numbers, canceling out the seconds, we end up with 181 meters, and that is the displacement in the x direction. And we have just filled out the table. We can now answer all of these questions here in the problem. So let's clean this up a little bit. So part A asks, what is delta r? Let's use the vector of delta r to figure it out. We know now that delta x is equal to 180 meters. We want to get the magnitude there, so delta r, that's equal to the Pythagorean theorem of delta y squared plus delta x squared. Now let's plug those numbers in and see what we get. So we plugged our numbers in, and we've figured out that delta r, the distance from start to end, the straight line distance, the magnitude of the displacement vector, 207 meters. Got that one done. Now the last two questions, they're both about the final velocity. What's the magnitude, the speed, right before it strikes the ground? What is the direction of that final velocity vector? So let's look at the vector final velocity, and we'll figure that out since we know the two vector components, v final x and v final y. So here's our final velocity vector, and I've put in the component values from the table you can see for Vx and Vy. Part B asks us, what is the speed right before it strikes at the end there? Well, that's to find out what is V, the magnitude. That's going to be equal to, using the Pythagorean theorem, we're going to have that's Vx squared plus Vy squared. Let's plug our numbers in and see what we get. And so we end up getting the final speed there right before striking the ground, 59.7 meters per second. Now for part C, they are asking us to figure out the angle of the final velocity vector right before it hits the ground, and we want to measure it from the horizontal. So here's horizontal, and it says below the horizontal. That means this angle. It's below the horizontal. Now, of course, we can do that by figuring out this angle, since we already have that triangle. To get that angle, we're going to go ahead and use our inverse tangent function, right? And so that's going to be the ratio of the opposite side, right? That's your opposite from the angle here. And here's your adjacent. Remember, I'm going to ignore all the signs and units, just drop them in there. And so opposite, 40, divided by adjacent, 44.3. Put that into your calculator and we'll get an answer. So we just figured out this angle, but the one we want is the one below the horizontal. So all we need to do now is go ahead and take the complementary angle here, 90 minus 42.1 degrees, and that is 47.9 degrees, and that is our direction below the horizontal of the final velocity vector.